Good morning, everyone. Carl Griffith from Graybar, and we're glad that you're here with us today on our G2 Talk webinar, where we're going to talk about what you need to know or should know about multimode fiber. We're going to talk about wideband multimode fiber, a very interesting topic. Before we get going, though, I'd like to go over a few things about the webinar. First of all, that if you're one of the first 50 people that are online here and you stay with us for the webinar, you'll get a certificate for a cup of coffee in your email from a large national coffee chain. This particular webinar can earn you a BIXI CEC or a BIXI credit. If you look at the bottom of the screen, you'll see a little blue ribbon down there. When we get to the end of the presentation, if you'll click that blue ribbon, there's instructions there that will tell you how you can download your certificate. There's a Q&A, so we're going to take questions with this webinar series today. So there's also a Q&A button. If you click that, a dialog box will open. Type your question in there, and we'll get it on our end. And then we'll go over those questions, as many as we can, at the end of the webinar. This presentation will be archived, and it will be archived on graybar.com, and you'll be able to go back and look at it again, or you'll be able to share it with your colleagues. So without any further delay, I would like to move forward. Graybar is all about buildings, and we're all about building, maintaining, and renovating buildings. And in this particular case, we're talking about primarily data centers inside buildings. At Graybar, we want to help our customers power, network, and secure their facilities or their buildings with speed, intelligence, and efficiency. And that's exactly what we're going to talk about today when we talk about networking and speed and efficiency with our data center facilities and what we can do to help with that efficiency. Our presenter today is Paul Colasar, and Paul is a engineering fellow with CommScope. He has a bachelor's in engineering and a master's in engineering. He got his master's from Fairleigh Dickinson University, and he's a terrific guy and an absolute wonderful fiber optic scientist. You'll get to know that here in just a minute. He worked at Bell Labs early on in his career from 1981 to 2001. He participates in all of the structured cabling committees that you would think and he's an optical fiber expert when it comes to this. So you'll see his name associated with iOS and IEC. You'll see his name associated with IEEE. He actually chairs the TIA TR 42.11 Committee on Optical Systems. One of the interesting facts about Paul and his career is he actually came up with the idea of OM3 and OM4 laser optimized fiber, and he helped conceptualize that whole thing and get it moving through the standards process and was a driver for OM3 and OM4, and he's been recognized by IEC for that effort and was given the 1906 award in 2011 for his work with laser optimized fiber. So I'm going to pass the presentation off to Paul. Thank you very much for joining us, Paul. We're looking forward to hearing as much as we can about multimode and the new technology that's before us right now with multimode fiber.
Thank you, Carl. Thanks for the introduction. Good morning, everyone. I hope today will be an entertaining time for you and an educational one. I want to first turn to the outline of the talk. As you see when it moves up on your screen, there are quite a few subjects here to cover. And the reason is that there's a lot of things that have come into confluence to drive towards a wideband solution. I will be talking about the drivers that have created the demand for bandwidth, to review some multiplexing technologies that are in use today and will be in use in the near future, talking about the benefits of the wideband multimode fiber in combination with short wavelength division multiplexing, looking at what this means to a cabling evolution roadmap, if you're planning your infrastructure, how this might impact your plans, looking at the bandwidth wavelength relationships of this new fiber, and taking a closer look at refining the use of those wavelengths to propose a wavelength multiplexing plan. Finally, we'll wrap up with transmission comparisons between OM4 and wideband fibers, talking about the standardization and demonstrations that have taken place. And hopefully at the end you'll come away understanding a lot more about what wideband is about than when you started. So let's take a look at the roadmap for data rates. The Ethernet Alliance put out this map earlier this year, and what it does is plot in the foreground the entry speeds of Ethernet, and as you go off into the horizon, it's increasing data rates as you go along. You can see there are many nodes along the way. Some of them are in green, showing the ones that have been standardized. Others are in shade, light shade of green, white, and those are in progress. And out into the horizon, you'll see nodes that may happen in the future, shown in white. Those are delineated on the right column. The reason we keep going off into higher data rates is because there's so much demand for bandwidth with all the mobile devices and greater command of data at your fingertips. It's just creating incredible amounts of need for pumping out data from data centers. Yeah, I'm sure you're all aware that applications that you commonly take for granted today didn't even exist 5 years ago. So there's a whole bunch of things that are coming into confluence, and we're doing our best with this technology, this wideband and short wavelength division multiplexing technology, to give you the ability to continue using multimode as the lowest cost means of getting optical connectivity in your data centers and your buildings. So moving on. Let's start taking a look at some of the multiplexing technologies. These are all being used today or will be used in the near future. The first one at the top is called time division multiplexing. This is where we take several low-speed data streams from, say, an ASIC device on a host, an IC that's processing lots of data. It usually operates at a subrate with multiple parallel lanes. Those will feed into a multiplexer, and the multiplexer joins all those lanes in time onto a much higher data rate, single lane. That is then used to go out over the fiber in what we call serial transmission. On the other end, the demultiplexer breaks that back down into the original lanes. The next step, when you exhaust that approach for serial data rates, the next step is to go to parallel fibers. And this is called space division multiplexing, or otherwise known as parallel optics. In this case, you simply add more lanes. I'm sure you're all aware that's how many of our highways are constructed, lane by lane as the demand is increasing. That has practical limits, both in highways as well as with fiber optics. So there are other ways of using the lanes more efficiently. The last one on the page at the bottom is wavelength multiplexing, where you take different colors of light, combine them optically into a single fiber, and then at the other end break them back out into their individual colors. This is akin to using an HOV lane, where you now have multiple people in every car. That's like multiple bits of information in time traveling together. They don't mix together. They're sitting in their cars, and each car is now carrying more capacity. Think of it that way. So these have been deployed from the top to the bottom in that order and time, and it's now time to start seriously using the one at the bottom for multimode transmission. As I'm sure you're all aware, wavelength multiplexing has been widely used for single mode transmission in the outside plant for many years. So let's take a closer look at the trends in the time division multiplexing. This is basically you're taking whatever you're multiplexing up to whatever data rate the current technology can handle, and there are physics limitations as to how fast you can drive a single lane. Today's maximum data rates are per lane around 25 to 28 gigabits per second. And we are going into a new generation of higher lane rates, or higher throughput, I should say, going into the 50 gig and 56 gig arena. But that's going to be done, it will be done with serial transmission, but it's also going to use the technique of more efficient encoding. So it's not just speeding up the bits, but it's putting more bits per symbol onto the medium. And the way that's done, you can think of it like languages. If you ever noticed when you buy something that has labeling in 2 different languages, and you read the English language and, for example, the Spanish language, and sometimes it looks like you can say things in one language much more compactly than you can in another. Well, it's similar to that, where you were using a more efficient language to convey the information with these higher data rates at the 50 gig lane rate. So that will be something we can employ for both multimode and single mode. And I'm looking towards 50 gig lanes to come out in products perhaps in 2 or 3 years from now. So in the meantime, we're going to be harnessing the serial data rates that we have today, and the way we solve that going beyond those rates is to go to parallel optics today. I'm sure you're all familiar with the use of 40 gig Ethernet with 4 lanes in each direction, each one carrying 10 gig. 100 gig Ethernet used the same approach. It's now evolved to 25 gig lanes in each direction. So we've gone from 10 lanes to 4 lanes with 100 gig by speeding up each of those lanes from 10 to 25. 128 gig fiber channel is very much like 100 gig Ethernet, 4 lanes in each direction. And as we go to 400 gig, we are now going to employ 16 lanes in each direction of 25 gigabits each. And you'll need a new connector, which is shown here in the middle of the page, called the MPO16. That has just completed its standardization in TIA as of the October meeting. Clearly, you can keep going, building up more and more lanes, but it becomes an impractical situation to continue to drive more and more cost into the cable plant. So we need a better solution, and it's clear that 100 gig SR4 is going to be more practical than SR10 because it reduces the number of lanes. Once you get above 16 lanes, as we're shown here, it really it becomes a diminishing appeal. So we're looking for a better approach to keep the multimode fiber solutions cost effective, and that's where shortwave division multiplexing comes in. So what do we do with shortwave? Where are the trends in that today? Well, the very first thing that came out in a proprietary way was Cisco's 40 gig BiDi transceiver, and that uses 2 wavelengths on each of the 2 fibers. Each fiber's carrying these wavelengths in opposite directions, and each wavelength carries 20 gigabits apiece. So you get 40 gig transmission on a pair of fibers, but the unconventional thing about it is that the wavelengths are traveling in opposite directions and sharing the fiber in opposite directions. However, it's important to note that the wavelengths of choice are 850, which is the legacy wavelength for all of the multimode applications, the mainstream applications, and they're adding a new wavelength of 900. And the important thing to realize there is that it's going towards longer wavelength. And I'll make it clear as to why that's the right choice as we go through the slides. Now, you can use wavelength division multiplexing not only in bidirectional means, but in unidirectional means. In other words, sending all the wavelengths in the same direction on one fiber and receiving them back on another fiber. As shown here in the illustration on the bottom of the chart, there are 4 wavelengths that are shown: blue, green, orange, and red. I'll be using these colors to depict these 4 wavelengths throughout the rest of the charts. But here we take 4 wavelengths, combine them into a single fiber, and break them out on the other end. And those 4 wavelengths, we're going to investigate what should those wavelengths be, and therefore how do we write a fiber standard to accommodate those wavelengths. Now you can take all these multiplexing techniques and combine them together, as I've shown here in this chart. So on the left, you've got time division multiplexing, taking groups of 4 lanes, speeding them up onto a serial lane which drives the lasers. The lasers are of 4 different colors. Those are optically multiplexed together and driven over a single fiber to the other end where the process is reversed. So here we have a bit of time division multiplexing and wavelength division multiplexing, and you can also imagine using this in parallel as well, so increasing capacity by using not only wavelengths but also parallel fibers in combination. Now it's interesting to note that the colors of the wavelengths the colors of the lasers on the left are distinctive. That's because each one needs to produce its own characteristic wavelength to be separable from the other wavelengths. But on the right, the detectors are all shown in gray, and that's because a common detector can be used, a common material system, common detector, monolithic detector could be used to detect all of these 4 wavelengths, and that will help keep cost reasonable. Okay, on we go. So what are the benefits of moving in this direction? Well, firstly, you have to realize this is really a combination of 2 things that are coming together. Shortwave division multiplexing is the technique for getting more information across each fiber. Wide band multimode fiber is a way of optimizing that technology to get the most out of it. So what we do with wavelength division multiplexing is reduce the number of fibers, and that's a good trend for improving multimode fiber's utility. Now, but we have to realize that using wavelengths outside of the traditional 850 nanometer legacy wavelength, it becomes more constrained when employed or transmitted on OM3 or OM4 fibers at high lane rates. What I'm talking about there is like 25 gig, 50 gig lanes. So we really need a fiber that can optimize those high-speed lane rates, which are the ones that are right around the corner for your deployments, so that we can get the most out of this technology. The idea being to support at least 100 gigabits per strand of fiber to at least 100 meters. Now, if you can achieve that, you'll be able to do the following things. First, support the legacy applications. So you can use this fiber as if it were an OM4 fiber and have additional applications that will play better on it for shortwave division multiplexing. We need to increase the capacity of that fiber to 100 gig per strand. By doing so, we'll be able to reduce the fiber count by a factor of 4 because each wavelength takes the place of a separate fiber, and it's all driven over a single strand. And if we can do that, we can enable things like single strand, or I should say single pair 40 gig Ethernet, single pair 100 gig Ethernet, and we can enable 400 gig Ethernet over 4 pairs, where today it will take 16. And in fiber channel, similar things. For 128 gig fiber channel and 256 gig fiber channel, both of those could be envisioned to go over a single pair. So doing this will extend multimode's utility as the universal medium for short reach applications and keep the cost as reasonable as possible when you need to move to optical connectivity. So let's move to the next slide. Here's a example roadmap. What you can do with shortwave division multiplexing and enhanced by wideband fiber. If you look down the left column, you'll see 3 data rates for Ethernet: 40 gig, 100 gig, and 400 gig. And as you move across the columns, those blue dashes represent the number of transmit and receive fibers needed for each lane rate. So as you can see, we can move 40 gigabit to a single pair going to WDM, and that is all the way over to the right column. Each of those dashes now having 4 colors, implying the 4 wavelengths. Similarly, for 100 gig, we have already evolved from 10 fibers in each direction to 4, and with WDM, condensing that down to a single pair. 400 gig goes from 16 fibers in each direction to 4. Now, what this means is you can imagine for a migration path to be able to run 10 gig from today, which you'll be deploying today, and moving up to 40 gig and then 100 gig on the same single pair infrastructure. Now, it's important to realize that if you plan to use 40 or 100 gig as a breakout interface, that is, to be able to separate the individual lanes, taking advantage of the fact that those transceivers present a much denser faceplate and a lot higher bandwidth switch, you have to remain with parallel fibers in order to get that breakout function. So these two things are going to coexist. Parallel optics, as defined in the standards today, as well as SWDM and wideband fibers, depending on how you want to use that 40 gig or 100 gig interface. And so please just keep that in mind. This does not replace parallel transmission, because in breakout scenarios, you're going to still need separate fibers for each lane. When we take a look at fiber channel applications, we see a similar roadmap. Again, going to 2 fibers, single pair transmission for both 128 and 256 gig fiber channel. Okay, hopefully that's clear. Now let's take a look at the framework that we are working within to establish standards around this technology for the wideband fiber. First, we have to understand what's the wavelength range we need to support. Now, the wideband fiber spec is going to define the fiber properties. It's not going to define the wavelength plan per se, but we need an agreed upon wavelength plan in order to decide how to specify the fiber. So that's what I'm going to present to you in a couple of slides, how we came up with the wavelength plan. Now, what went into the wavelength plan were a number of considerations. First, in order to support legacy applications, that dictates that one of the wavelengths has to be 850 nanometers, plus or minus some tolerance. Second, we want to move towards longer wavelengths, like BiDi did, in order to gain improvements from lower chromatic dispersion, lower attenuation in the fiber, and the ability to even get faster VCSELs as you go to longer wavelengths. That's just a natural consequence of VCSEL design. So we also need to be able to support at least 4 wavelengths, because that's a natural replacement for the 4-lane parallel applications that are there. So we want to convert each of those separate strands of fiber into a separate wavelength. That means there needs to be 4 of them. Now, talking to the transceiver vendors, and we started talking to them long before we brought the proposal into TIA to standardize the fiber, we heard consistently that the vendors wanted to have wavelength separation of at least 30 nanometers. So the reason they want that is because it accommodates low-cost manufacturing, the ability to have temperature variation without having to thermally control the transceiver. And that is, what I mean thermally control, I mean active cooling, like a thermoelectric cooler in the device, which would drive up cost. We also need to consider the spectral width and the fact that we want to have low complexity filters for the multiplexer and demultiplexer. All of that is in line with trying to keep this at lowest possible cost. Now, we take all those facts, put them together in the next analysis to determine the shortest wavelength range, the shortest wavelength and the wavelength range over which we have to operate. So here's some key information about the way multimode fiber works. trying to meld in those 4 wavelengths at 30 nanometer separation. Those are shown in those dashes across the top of this chart, the blue, green, orange, and red dashes. And you can see those are separated in wavelength by about 30 nanometers. Now, the properties of the OM4 fiber there are shown in the various lines on the graph. The modal bandwidth, the worst case modal bandwidth of the fiber, is shown in the dashed blue line, and you can see that peaks at 4,700 megahertz, which is the key specification for OM4 fiber. It falls off rapidly to either side, or I should say it can. This is showing a worst case scenario. The red dash line represents the chromatic bandwidth, and as you can see, that increases as it goes towards longer wavelengths. Now, if you combine those 2 bandwidths together, the blue dash and the red dash line form the purple line, the solid purple line. And as you can see, because the chromatic bandwidth is increasing with longer wavelength, that purple line has a higher bandwidth as you move towards the right of its peak compared to the left of its peak. Now, what we need to do is to provide a fiber that gives you a total bandwidth, that purple line, that is at or above that black flat dashed line. It's running around 2,500 megahertz kilometer. That's the worst case bandwidth at 840 nanometers. If we can provide a total bandwidth of that magnitude across the whole wavelength range, it will be superior to OM4, and it will deliver equivalent bandwidth across all those wavelengths. So that's the objective of the spec. So now we consider, what is the wavelength plan? We got to fine-tune the wavelength plan. We can come up with an initial concept where the first wavelength is 850. That's the center of the first wavelength band. Then there's 30 nanometer separations for the next 3, meaning 880, 910, and 940 nanometers. That's the rough idea. Now, when we looked at the details, we had some refinements to propose, and this chart goes through the details of that calculation. I won't belabor the details, but I will tell you that we've considered VCSEL tolerance, VCSEL manufacturing tolerance, that is the ability to manufacture VCSELs on the wavelength target, the variation of that wavelength of operation over temperature, and the spectral width of the source of the laser itself. We also made sure that we had at least 30 nanometer separation between the operating bands, and we in order to use the spectrum most intelligently, and we used a wavelength scaling approach where the pass bands and the guard bands were scaled with wavelength in order to have equal filtering capability at all wavelengths without penalizing any, and getting it into the smallest spectrum possible. And when you go through all that analysis, you come up with the chart on the next slide. All of the parameters of the pass bands and guard bands are provided in the table. And as you look down the table on the right 2 columns, you'll see that the pass bands and guard bands are increasing systematically as we go up in wavelength. And that's what I mean by wavelength scaling. That means the spectrum is used equitably for all the bands, and there's no one band that is penalized or needing a more severe constraint for its filtering than another. The nominal wavelengths are now shifted up slightly from the basic concepts. And what I mean by that is the first pass band, the blue one, is no longer centered on 850. Instead, it's been moved up about 3 or 4 nanometers. And it ends up that the shortest wavelength in this plan is 846 nanometers, and the longest wavelength to the right of the red passband is 953 nanometers for a 107 nanometer range. So that's the target for the standardization of the fiber. We need a fiber that will ensure the sufficient amount of total bandwidth from 846 to 953 nanometers. And this is a plan that the transceiver manufacturers involved in the standardization have said it was a reasonable plan. So we are moving in that direction. So let's take a look at the next chart. Now, this chart shows several things. There are three different lines on the chart. The green one, the one that kind of runs in the middle, is what is needed from the modal bandwidth of the fiber in order to close the link models that we have set as objectives in the standardization process. So what you'll see is, as you move up in wavelength, that the bandwidth requirement of the fiber can be reduced. And that's the modal bandwidth. Remember, we're trying to keep a constant total bandwidth, but that's a combination of the chromatic bandwidth and the modal. So this is a chart of just the modal bandwidth. And the modal bandwidth can drop because the chromatic bandwidth is rising, not shown here. So the green line is what we need to achieve our objectives. The blue line is what you will be able to achieve and guarantee with an OM4 fiber. And as you can see, that drops below the requirement as you go above, say, 875 nanometers. So we are needing a new fiber spec that ensures we are remaining above the green line, and the red line with the hump in the middle is an example of a fiber that meets that spec. So we're going to now look at what kind of transmission comparison we see between OM4 fibers, the kind of blue line fiber, and the red line fiber. The way we look at these transmission differences is with a setup like this. We use a BERT, which stands for Bit Error Rate Tester, and what it does is drive a laser. And you can drive a laser of different colors. Shown here is lambda A, lambda B, so forth. That laser couples into the fiber under test, FUT. So you can put into there an OM4 fiber or a wideband fiber or whatever you would like. You can put, after the fiber goes a variable optical attenuator. And what that does is allow us to vary the amount of power that reaches the receiver. And by varying the power, we can decrease or we can see the effect of and the relationship between the received power and the generation of errors. And so we make plots of bit error rate versus received power. And if you plot these things for various fibers, you can get a good comparison of how different fibers behave with different wavelengths. And that's what I'll show you on the next chart. So there's two charts here. The one on the left is the bit error rate performance with transmission at 850 nanometers. That's our legacy wavelength. The one on the right is transmission at 980 nanometers. Now, you're saying, why 980? I thought the spec was 953. And this was some early data taken, probably a year ago or so, that where we were using what was available at the time, and 980 nanometer VCSELs were available that could operate at 25 gigabits per second. So we're transmitting at 850 and at 980 over 100 meters of fiber, and we're comparing two different kinds of fiber. There are 5 lines in each chart. The one that is the baseline is called the back-to-back measurement, and that's without any fiber of any length to speak of in the test. And that is the black line with the crosses, the X's. You'll notice all the other lines fall to the right and above that line. Anything moving to the right and above is showing an impairment, an added impairment from the inclusion of the fiber in the transmission test. At 850, there are two OM4 fibers which show very low amounts of impairment. Even after putting in 100 meters, they are almost the same as the back-to-back. The wideband fibers show a bit more impairment, maybe a dB or so of additional impairment. They needed another dB of power, or maybe something like 10% more power to provide the same bit error rate performance. Now compare that operation of 850 to the one on the right at 980. At 980 nanometers, we again show the back-to-back being the long black line there. The two OM4 fibers have now moved far to the right and upwards. In fact, the magenta line is so far over, it couldn't, no matter how much power we provided, it couldn't provide a reasonable bit error rate performance. And that's because OM4 fiber is not optimized for 980 nanometer transmission. However, the two red lines, which represent the wideband fiber, show only modest increase. I think they go from 1 dB at 850 to 1.5 dB at 980. Keep in mind the scale on the x-axis has now changed. Each division is only a half a dB. So that shows that the wideband fiber is indeed a superior transmission medium for longer wavelengths. And that's the key to improving its performance to make sure it's optimizing the capability of shortwave division multiplexing. So let's take a gander at some of the demonstrations of this technology that we've been involved in over the past 9 months or so. Back in March at OFC, we showed, I believe, the first public demonstration of a prototype 100 gig transceiver. This is a Finisar prototype. In the right photo, you can see it in the foreground. It's actually a stack of 4 boards that are individual SFP transceivers. So each one of those is a single wavelength. Those are combined externally into using an optical mux and demux into a set of fibers on those spools. There are 3 spools, each with a different length of fiber totaling 225 meters. This demonstration successfully placed over 100 gigabits per second through a single fiber channel, concatenation of those 3 spools, and it ran error-free over 225 meters without the assistance of forward error correction. And it's important to know that at 25 gigabits per second per lane, which is what this is doing, forward error correction is now a standard feature defined by IEEE. So if that had been turned on, forward error correction would have allowed even longer reaches and more robust transmission. But it was robust. It sat there for the entire duration without generating any errors. So that was a remarkable situation, 225 meters on the wideband fiber. We also have taken these demonstrations to other trade shows. For example, this fall at Bixby, we were demonstrating another Finisar transceiver, and this one is a QSFP, fully integrated, able to do 40 gigs with 10 gig per wavelength, and we were able to transmit 500 meters over the wideband fiber. We next went to ECOC in Spain in September, and at that time, Finisar's transceiver that we showed from OFC was now fully integrated into a QSFP. It performed even better. We were able to go 300 meters without FEC at that show, and we did the same thing at GITEX in October. So this is clearly showing the transceivers are emerging, the fiber is emerging, the cabling system, and so we believe that this entire package is ready for standardization. And in fact, we have announced our cabling system at the fall Bixby. The laser speed 550 wideband multimode fiber shown here in the center in chartreuse. is the first, as far as I know, of cabling systems to enter the market with its availability in November. So it is now available. There were a number of press releases about it, and in fact, along with this Bixie show, there was also an announcement of the SWDM Alliance. We are charter members of that, and you can go to swdm.org to see that website. There are probably 10 or 11 companies involved in that alliance, including transceiver manufacturers, fiber makers, cabling folks, and who else? Oh, systems folks, like switch manufacturers. So the whole ecosystem is starting to gel around this concept of SWDM. So that's all of the work in the background. In the forefront, we are moving rapidly to standardize this fiber. It was only about a year ago that we had our initial presentations to TR42, and we brought in contributions co-authored by fiber, transceiver, and systems companies. It launched the initiation of a standardization project at that meeting. There was no company that was against moving in this direction. We have broadened this participation in the standardization process to include members of the international community through IEC 86A. That brought in a number of fiber manufacturers that are offshore, and we have monthly meetings by teleconference as well as face-to-face meetings every 4 months. It's been a very lively set of discussions, seeing over 40 contributions over the past year. We have progressed the standard through its first ballot, and in October we authorized the second ballot. I foresee the standard 492 AAAE to be published in 2016. And as we publish that document, it will then be referenceable by the applications groups in IEEE that do Ethernet and in T11 that do fiber channel. So we're preparing for proposing this fiber to them as a means to advance multimode technology in the higher data rates that are coming. So, to summarize, the industry is moving to utilize shortwave multiplexing. We see it in all parts of the ecosystem that need to come together: transceivers, fibers, cabling, and system vendors willing to use it as well. It's going to optimize the reach of short wavelength division multiplexing while it maintains the support for legacy applications equivalent to OM4. And we're going to, by standardizing this, we're going to provide ourselves the opportunity to go into Ethernet and fiber channel and propose this new media and this new technology to define better solutions or alternative solutions to the parallel optics that are going through the standardization process now. And when we achieve this, we are going to extend the utility of multimode fiber, continuing its legacy of delivering lowest cost optical solutions. And with that, I'd like to thank you for your attention and turn it back to see if there's any questions.
Paul, I want to thank you very much for your presentation today. Before we get to questions, though, I would like to talk a little bit, if you don't mind, if you can give us a little bit of information about the value proposition associated with moving from traditional OM4 into this new optimized fiber that allows us to do shortwave division multiplexing and come up with this wideband solution that you've described here, which was absolutely excellent. I can see some obvious ones in terms of the fiber count being reduced, and maybe the connector being less complicated than having an MPO that you have to deal with 16 connections for fiber. I can see those, but what are some of the other value props that are available to consumers when they move from the older OM4 technology to the optimized new technology that takes advantage of wideband multimode fiber?
Well, you mentioned the big ones. I mean, we're going to see a more efficient use of the cabling infrastructure. That implies a lower cost cabling infrastructure to do the same job. At the same time, when I earlier mentioned that you could combine this SWDM technology with parallel, that means the cabling infrastructure also can go into higher data rates than it could before with a solution, say like an SR4 solution, where 4 fibers in each direction will now potentially get you to 400 gig, and if you were to go to 16 in each direction, you'd be looking at 1.6 terabits over multimode fiber. So it not only makes a more efficient solution, more cost-effective, but it also opens the door to data rates that would be otherwise impractical over multimode.
But what I noticed in the presentation, we talked about this shift to optimize the fiber, where on the low end, we moved it up 3 nanometers, and then on the high end, it also moved 3 nanometers. But it seems to me that the new fiber possibly could be backwards compatible. Like you could deploy optimized fiber for wideband multimode fiber today and use it traditionally, but when you got to 100 gig, for example, your fiber plant's already ready for 100 gig with less connectivity. Am I right in my assumption there about this backwards compatibility?
Yes, that's one of the foremost goals we have of, and which the current draft standard is in line, is to be able to support all the legacy applications as if it were an OM4 fiber. And that means whatever specs OM4 support, this fiber will also. And then from there, as you mentioned, being able to open up the possibility of optimizing the use of SWDM solutions going towards higher data rates. So you hit it right on the head. That's exactly one of the main pillars under this fiber, was that you could install it today, use it just as if it were an OM4 fiber, and then realize benefits as you deploy SWDM for 40 gig or 100 gig or beyond to make sure that you can get the farthest reach or support the most complex cabling topologies, in other words, patch panels and so forth, to get you from point A to point B. When you use an OM4 fiber or an OM3 fiber with SWDM, you will still get higher capacity out of the fibers, but you will not get as much reach and you won't have as much power budget because you're going to be seeing impairments at the longer wavelengths, which will limit the capability of those fibers more so than with wideband fiber.
Great. That makes me feel a lot better, Paul. Before we get to our Q&A, I wanted to remind everybody that this presentation will be archived. You can go up to graybar.com and click on the G2 Talk webinar, and you can get this presentation, and you can look at it at your leisure, and you can also share it with your colleagues. There'll be a URL up there that you can share. If you're one of the first 50 people that are online with us today, you'll get an email a little later with a barcode on it that you can swipe at a big major coffee chain and get yourself a cup of coffee today. I wanted to remind you all that there are Bixby credits associated with this presentation. And at the bottom of your screen, you'll see a little logo down there, or a little symbol that looks like a blue ribbon. And in just a few seconds, you'll be able to click on that and begin downloading your certificates. I wanted to remind you that there was a Q&A button at the bottom of your screen. If you click on that Q&A and type your question into the dialog box, we'll respond to some of these questions as we complete our hour. I would also like to offer to everybody that's online, I'll make this offer to you today. We have a really nice white paper from CommScope. I'm sure that Paul was the major author of this, although I don't see his name that appears on it. But anyway, Paul's got a white paper here that goes through this in a printed format. If you would like a copy of this white paper that describes the technology that Paul just went over on the webinar with you, if you'll go to the Q&A button and you'll type in the letters WP, or you'll type in the word white paper, I will email you. I will email you this white paper and you'll get it later today. So if you'll just type in WP or you'll type in white paper in the Q&A dialog box and hit send and get it to us later today, I'll send you this white paper. Paul, if you don't mind, we've got a few questions that have come in and some of them are really good. You mind taking a few questions here for a moment?
Go right ahead.
All right. The one that I noticed that came in earlier came in from Tim, and let me see if I can get it up on the screen here. Tim came up with a question about testing, and I thought it was very appropriate here. He said the existing cable standards have field testing parameters for the normal wavelengths of 850 and 1300 nanometer fiber. With use of longer wavelengths for WDM or on multimode, do we expect to see different field test equipment because of these different wavelengths?
Great question. Similar questions have been raised in the standardization process, and I'll give you the answer as I see it and tell you why. My view is that we don't need any new wavelength tests in the field. The reason is that 850 nanometers represents the highest attenuation wavelength of the group of SWDM wavelengths. And so you will measure, if you measure at 850, you're going to see the greatest amount of attenuation, and the attenuation of the connectors is also, at least multimode, is fairly independent of the wavelength, although it is worse for 850 by a small amount than it is at 1300. So if you are measuring the cable plant at 850 and it passes, it will also pass for the other wavelengths. Now, the reason the cabling standard has a 1300 nanometer requirement in it is because the fibers are more prone to bending loss at longer wavelengths. But it turns out that the fibers we're talking about, and we're talking about 50 micron bend-insensitive fibers here, they have about the same bend loss properties at 950 as they do at 850. So the reduction in bend loss efficiency at 1300 nanometers does not show up at at 950. So again, there's no reason to have to measure these fiber cable plants at anything other than the wavelengths that have already been standardized. Great,
thank you. Tim also asked this question: do you anticipate CommScope will be working with the fiber cable manufacturing community to develop a new multimode fiber that is optimized for wideband multimode fiber? I think you alluded to that in one of your slides near the end. I believe CommScope's fiber vendor has some product available. Is that correct?
That's correct. There's at least two vendors of multimode fiber that have announced their availability of wideband fiber. So we already see, before the standard is finished, products of this sort on the market. We are providing a cabling system using that fiber, and as I mentioned, it's called Laser Speed 550 wideband. So it's already available. Then we're talking about trunk cables, fan-out cassettes, patch cords, and so it's a real thing already.
Jason asked this question about the cost associated with the new optimized fiber. do you anticipate a cost premium with the new fiber?
This fiber is more difficult to manufacture. It has higher specification, so the cost of the fiber is higher, but there is savings because you don't need to use as many strands, moving to 40 gig and 100 gig. You will have a factor of 4 reduced amount of strands in each of those channels. So that more than offsets the increase in cost of the glass per strand, if you will, because you use many fewer strands.
Calvin asked this question. He said that single mode fiber with dense wave division multiplexing technology has long achieved high data rates and far reach. Will pricing for single mode systems come down shortly to make it more attractive than wide band multimode fiber? What do you think about that?
Well, here's the thing. There is always pressure on the single mode transceivers to come down in cost. Multimode transceivers usually, and especially at 40 and 100 gigs, started out with very low cost, while their single mode counterparts were astronomically costly. That price premium has narrowed, and you can find single mode solutions that are relatively competitive. But the thing is, you got to look back at all of the applications that are already running in your data centers and your enterprise. And you will, if you go to single mode, you will either have the choice of leaving all those legacy applications behind, in other words, stranding all that equipment, or having to run both a multimode and a single mode infrastructure. So wideband is one way of getting a universal medium in place where you can support all your legacy applications. And most data centers have 2 or 3 generations of applications running at the same time, anything from 1 gig all the way up to 40 gig at the same time. And so this is one way of having a universal solution, staying on a multimode fiber infrastructure, which, by the way, has a lot greater tolerance for connector contamination than single mode. One of the things with single mode is you have to be very meticulous about connector cleaning. And you get much more forgiveness with the multimode because it's a larger core. And so you weigh all those things together, and it's not the case where, you know, one answer fits all. But what we're doing here is providing a means of using multimode more efficiently to both support your legacy and your future applications in the lowest cost possible way. So hopefully, I mean, everybody has to weigh the situation for themselves, but this, we believe, is going to be a very attractive solution and make economic sense to a lot of customers.
Thank you, Paul, for asking that question, or for addressing that question. I appreciate it very much. We're getting close to our 1 hour, so I'm going to kind of wrap things up. If you have a question, please type it in the dialog box and send it to us, and we'll respond to your question via email. We'll leave the application up so that you can ask some additional questions for a few minutes, and you can download your completion certificate if you want to get your CEC. So we'll leave the application up for just a little while so that you can do that. I encourage you to take advantage of the archive that's on graybar.com if you would like to share this presentation with others. So I want to thank you, Paul. It's been a great webinar. I appreciate the time that you spent with us today, and I want to thank our attendees that were on the G2 Talk webinar today for joining us. We look forward to for you to be with us again next month for another G2 Talk webinar. Thank you very much and have a great day.
Thank you.